All right. So, we will so far we dealt with equilibrium systems. Okay. Statistical physics equilibrium we are doing, where we are looking at equilibrium properties of phase transition. I did not do many calculations, but even quantum field theory, lot of as long as you assume Green's function and Collinson function are equal, time is not playing a role. So, then we solve equilibrium. Okay. So, now we will go into non-equilibrium. So, here things will be dynamic, things will change in time. So, we start with Langevin equation. So, today I will illustrate one example Langevin equation which is time dependent. So, let us first look at review the properties of equilibrium systems which we discussed in this course so far. So, equilibrium system time does not appear explicitly. So, if you recall when I was doing phi 4 theory, I just turned off d by dt of phi is 0, right, I had turned this off. So, you are looking at only the equilibrium properties of phi 4 theory. This is used for studying for many things like equilibrium stat mech, phase transition and some quantum field theory, okay, which I did not do a lot of examples, but most of lot of things can be done with equilibrium framework. For example, even superconductivity will be equilibrium framework, but if you are looking at conductivity, quantum conduction, then that will be non-equilibrium. Okay. So, I think it will become clear when I give some examples. So, for equilibrium systems GK is CK, I in fact showed it well, demonstrated using an example. So, Green's function and Collinson functions are same, and it is not time, it is not we do not have frequency dependence on this, omega was not there, okay, this GK or time dependence we do not have it, and detailed balance is respected. So, energy flux or energy transfer from one to other is 0. Okay. Non-equilibrium systems, time will come explicitly. Okay. So, if I were dealing with phi 4 theory, then I had to worry about this d by dt of phi. So, this will be like this phi minus phi cube plus Laplacian phi. So, this phi d by dt will be playing a role. So, I had to write phi as function of x, well, k and omega. So, wave number k which we used to do before, but the frequency will also come into play. Okay. So, system will evolve in time. A Green's function and Collinson functions are functions of time, okay, functions of time. Gk is not same as Ck. So, in fact, we will have Gk omega. Okay. I will give an example in today's class itself. When frequency comes, then things are different. Detailed balance is typically not respected. Sometimes it may be, but in general it is not. Energy flux is not equal to 0. There will be energy transfer across scales or across it could be in real space itself. For example, in conduction when heat is flowing from, so this hot region and cold region, heat flows like that, no. So, this is heat flux and that makes it non-equilibrium, right, because heat is going from left to right. Had it been equilibrium, then what goes from left to right should also be equal to right to left and they should cancel. But for non-equilibrium there will be a one direction of energy heat flux or quantum flux and so on. Okay. So, we will deal with I am going to introduce Langevin equation. So, Brownian motion everybody is aware of. So, I will, so Langevin equation describes Brownian motion or motion of a this particle in a background of atoms and molecules. So, these black dots are molecules and this red dot is red block is some dust particle or pollen. Okay. And please keep in mind that this system is, there is no mean velocity, hydrodynamic velocity. So, it is not like atmosphere where there is a hydrodynamic velocity. This is at small low temperature where things are, I mean the water is still, and if you put a pollen particle or some light particle, it will jiggle around. You can see this movie in Wikipedia, it is nice movie, it moves slowly. So, you have to see there is a difference, the speed of the molecules are very large, speed of sound, but speed of this yellow particle is pretty small. Okay. It is like, in fact, it is hydrodynamic velocity, but it is viscous regime, is a small velocity. Okay. So, how do I model it? So, let us look at let us model in the viscous regime. So, we start with the Navier-Stokes equation, this is the Navier-Stokes equation. So, the velocity u, so you think of this u as the velocity of this yellow particle. I am making only motivation. So, the is in the background, I think I will not say, I will take back, I will just say that this you have to model particle in a in the background of a viscous fluid. Okay. So, there is a derivation with the boundary condition. No, I mean you might have seen this derivation, a cylinder and there is a flow going around the cylinder, then how much is the force acting on it. Okay. So, this derivation we will not do it here, it is too complicated, but I will state the result. So, imagine, so one thing is to keep the body fixed and the flow coming from the left, or flow is at rest, fluid is at rest and the ball is falling or ball is moving with some velocity. So, what is the drag force acting on this particle? Okay. So, the total drag is, the one component is proportional to the velocity v, gamma v. So, this is a linear drag or viscous drag, other one is v squared, turbulent drag, this comes from this part. So, if you ride a bicycle with very high speed, then it will be v squared, but if you are riding slowly or very slowly, then it is gamma v. Okay. So, we will stick to the regime where this approximation is good and we will drop the v square term. So, the force is mass times gamma u, u is the velocity of the particle in the background of the fluid. Okay. Now, the derivation which I am skipping, it is 6 pi mu r u. Okay. Mu is a dynamic viscosity and r is a radius of the sphere, a radius of the particle is treated as sphere and that is thing. So, at least I am sure you are aware of this formula, we may not know the derivation, but this formula you may be aware. Okay. So, we are going to use this formula. Of course, this velocity u is not constant velocity, this velocity u is changing with so this particle in the yellow particle in the background will be just getting kicked around like that. Okay. So, it is random motion, but so we will have to model the random part as well, but during the motion it experiences this drag force. So, this simple equation first proposed by Langevin models this particle motion quite well. Okay. So, this part, this is acceleration which is proportional to the that viscous acceleration or viscous drag, and this zeta is a random kick, a random force whose average is 0. Okay. Just so, there is a noise which is kicking it, but average of zeta is 0. Sometimes it is from the right to left, left to right, bottom to top, top to bottom. So, it could be in any directions, no particular direction of force will be employed. Time average is 0, yes, time average of zeta is 0 of the force acting on it, but in statistical physics for ease of calculation we assume ensemble average. Now, ensemble average is that you have created lot of similar systems. Okay. We have instead of one system where we have this fluid and a particle moving around, we have 1,000,000 of them, and of course, all of them will behave differently because it is a different system, but we will do average of that, okay, and then look at velocity. So, this is ensemble average. Okay. So, ensemble average makes calculation simpler. So, this is supposed to be ensemble average. So, if I do ensemble average, then zeta average is 0. So, we will get this, and it has a very trivial solution, right. It is a linear equation for ut averaged, and its solution is exponential in time. So, this is the average initial velocity e to the power minus gamma t. So, if this particle slows down, but this slowing down is for short time. This gamma is a, so this viscous force is pretty strong. Okay. So, gamma is gives you the inverse time scale, right. So, you can look at from here, the time scale is 1 by gamma. So, gamma t, so we will assume that gamma is large or time scale is small. So, kicking is getting kicked very often, okay. But on the whole it has certain drift, that is what I am going to derive in a while, but when it gets kicked it will move because of it has been injected some initial energy or the energy during the kick, but because of viscous drag it is going to slow down. So, this is slowing down because of the viscous drag, okay. But then you will get another kick. So, then it will again get a bump of speed, then again slow down and so on. So, it does not have constant speed, it just keeps getting jump, drop, jump, drop, jump, drop like that, and this for short time. But now we want to see the long time behavior. Okay. Now, long time behavior, let us look at the position of the particle. So, to get the position, let us start with this r squared. I am not really interested in its isotropic system, no, it can be going any direction is equally probable. So, we look at r squared and d by dt of r squared by 2. So, what will that be? So, take the derivative, r is a vector. So, r dot dr by dt, right. So, that will be u. So, that is r dot u. You take another derivative. If I take another derivative, what will I get? D square by dt squared of r squared by 2. So, r dot u plus r u dot. R dot is u, right. So, the first term in the right hand side becomes u squared, u squared, right, u dot u. The second term is r dot u dot, u acceleration, and acceleration is minus gamma u plus zeta. Okay. So, now what is this guy? This r dot u minus gamma, but I know what is r dot u, it is d by dt of r squared by 2. Okay. So, you plug that in. So, this is replaced by d by dt of r squared by 2 plus r dot zeta. This is at my right hand side. Now, I do the ensemble average, I do averaging. So, if I do averaging, r is changing, of course changing, but changing slowly, but zeta is changing fast. So, if I do average of this, what will I get? 0, no, because r is changing slowly, adiabatic approximation. So, this will give you 0. So, we have two, right hand side has only 2 terms, not 3, and this is the first term here, and second term is here, and u squared I take it to the right hand side. Well, it is already in the right hand side, but I am taking this to the left hand side. Okay. So, this will give us how r squared changes with time, right. It is a second order equation, but it is easily solvable, it is linear in r squared. So, what is the solution? Homogeneous part and a particular part, and homogeneous part will be constant plus exponential minus gamma t. So, there are two parts, two homogeneous solution, right, second order. So, that is what I write it here. So, this is exponential part, okay, and so you try e to power m t, okay, that is, and find m, and one m will be 0, other one will be minus gamma, and the particular part is, so we let us try the solution which is r square is linear in t. So, this will give us a constant and this will give 0. So, linear in t satisfies the equation, and particular solution is unique. I am just doing it by guessing, of course, you can do by other tricks as well, but this is a particular solution. Just plug it in here, you will find the left hand side will give you u squared. Okay. Now, how do I determine C1 and C2? I get it from the initial condition. Let us assume that it starts from origin. So, at t equal to 0, r squared is 0, and also I need another initial condition. So, let us assume that d by dt of r squared is also 0. Okay. So, I will not do the algebra, this please put these two initial conditions and that will give you the solution like that. Okay. So, this is the exact solution of that equation for the initial condition given here. Okay. At t equal to 0, you can see that this becomes 0 and this becomes 0. So, r square is 0. So, initial condition is respected, but of course, I have to do the derivative as well, more algebra, but you can verify. Now, for short time I can short time what happens. So, which will short time is basically pretty uninteresting, right. I mean, this is too much jiggle, I am looking for long term behavior. Okay. So, short term I can expand this part 1 minus gamma t, okay, and then what happens, this will be 0. So, you go to the next order term gamma square t squared by 2. So, that will basically give you t squared, and what does it give you t, what does it mean r squared is going as t squared, right. If I do this, then this will cancel with this and I will get t squared. So, it is like a ballistic, right, a short time before the kicks, it is going with constant velocity for short times. But if you go for t bigger than gamma 1 by gamma, then the kicks are trying to negate its ballistic motion. Okay. Is it clear? I mean, for short time it is going with some velocity before it gets another kick. So, when it is going nicely happily, but well, poor guy, he just gets boom, one atom comes and hits it, then it gets what happened, then it moves in some other direction. But on the whole, for very long time, so t much bigger than gamma. So, I am looking for other limit t much bigger than 1 by gamma. So, this is going to 0. So, and t is very large, so 1 can be ignored. So, this is the term which is non-zero. So, r squared is, so this 2 I am taking the right hand side, 2 is squared by gamma, 1 gamma cancels with gamma squared. So, this is the thing. So, r squared is proportional to t, looks good, no? Does it, are you happy with this? this is a random walker, right. R goes to square root t in time t. Had it been ballistic, it would have gone straight t squared, but because of these collisions it is losing direction once in a while, well very often actually, not once in a while, but on the whole it is drifting away from the origin. So, R squared is proportional to t and this is a proportionality constant. Now, U squared is in a heat bath. So, this fluid is at a constant temperature and there are a lot of molecules. So, this our particle will be in heat bath, thermal equilibrium. Of course, temperature of this blob is same as temperature of the molecules, right. That is equilibrium, that is what it means. Temperature will become equal. If this particle was too hot, then it will transmit to the particle molecules and vice versa. So, its temperature is T. Well, it is a single particle, what do you mean by temperature single particle? But idea is that half mv squared of this particle is half kBT, but it is 3 dimensional. So, Vx squared plus Vy squared plus Vz squared in the left hand side. So, I have to put 3 here. Okay. So, mv squared is 3 kBT. So, U squared is 3 kBT by m. So, that is what I put it here. So, 3 times 2 is 6 kBT by gamma m. Kb is the Boltzmann constant. Now, Kb you may know that Kb is Rydberg constant by Avogadro number and gamma m is the viscous force. I can use 6 pi eta r, r is the radius of this particle. So, we put that 6 is cancelling with 6. The numbers we should not worry too much about these prefactors, but irrespective 6 is cancelling with 6 here and we get this formula. So, R squared is proportional to T and this coefficient is called diffusion coefficient, okay, diffusion coefficient. So, diffusion coefficient is proportional to temperature and is inversely proportional to the viscosity. Okay. So, this is a formula and who came up with this formula first? Who derived this formula first? Einstein. Okay. So, his 1905 paper, one of the famous papers, and that is why it is called Einstein relation. Now, Einstein used this formula to get Avogadro number. So, how do I get Avogadro number? So, this of course, he used an experiment, he did not do the experiment himself. So, the experiment D was reported, R was known for thermodynamics, temperature was known, eta was known for water, R estimated the molecule radius. So, n can be obtained from this. Okay. So, from the experimental data n was determined, he was off slightly, but he was quite on dot. Okay. So, this how the Avogadro number was computed for the first time and this is a good formula. Okay. I mean this is a very powerful formula. So, you can get diffusion coefficient from microscopic quantities. So, this is Einstein relation. So, in electric field, so the equation will be changed a bit. So, instead of this random force we put a constant electric field and this is also very easy solution. For short time the homogeneous solution will be important, but for long time only the particular solution will be important and particular solution will come by u will be constant, okay, by equating these two terms. So, by equate that two term you will get u d is equal to E by m E by gamma and this is the drift speed. Okay. So, electric field, so compute conductivity you use this model, I think Root's formula or something like that, okay. And this mu is called mobility, the coefficient in front of E. So, the drift velocity is proportional to E and the proportionality constant is called mobility, okay. And mobility is connected with D, right. D is kBT by gamma m, I derived in the previous slide. So, I just adjust these parameters and so on. So, the diffusion coefficient is kBT by E, electric charge E, multiplied by mobility. Okay. So, we can do quite a bit of stat mech by this simple model, Langevin equation. Looks interesting and looks very promising as well. And this equation is non-equilibrium. So, in fact, that leads to diffusion. So, if you have a bunch of particles near the origin, then these particles, so instead of one particle you put lot of particles, but then what will happen to this particle, because of each guy will drift, but they will go in different directions. Some of course try to come back, but on the whole you will find that this particle would be spread out. You can solve it. In fact, the diffusion equation is a good model for this process, and here it is changing with time. This density is changing with time, n is the density of particles. So, this is non-equilibrium. Now, the question is it, what about the atmosphere in this room? Can we model particle in this room, which some of it is invisible, but okay. Can we model particles in this room using Langevin equation? Great, yes. So, there is a nonlinearity that makes the diffusion equation not applicable. So, we assume in the beginning, recall this particle was assumed to be viscous, moving in a still fluid, right. The background was only the molecules which were randomly moving, but molecules in this room is not randomly moving. Okay. So, there is a random motion, but there is certain hydrodynamic motion because of AC and our breathing. So, it turns out there is a hydrodynamic motion, and the thermal motion is 300 meters per second, but the hydrodynamic motion is possibly around 1 meter per second, much slower, is averaged out velocity. Okay. So, it is a collective motion of these molecules because of various factors in this room. Okay. So, there are, in fact, this room is turbulent, the air in this room is turbulent, and the assumption breaks down. So, that is not going to work. So, Einstein relation is not, does not work in this environment. Okay. So, so we will get to that bit later, and that formula is not applicable here. So, in atmosphere, D from the Einstein relation is not valid, and the D for this room is this. Well, actually, if I know epsilon. Epsilon is the energy supply rate. So, we will discuss turbulence, we will come to that. So, in turbulence we have, in this room there is energy supply by the air condition and our body, heat. So, that kind of energy supply to the atmospheric gas here, that epsilon is coming here, and so this diffusion coefficient is function of L, function of the size of the vortex. It is not constant like Einstein relation. There is one diffusion coefficient. It turns out the diffusion coefficient will change with L. So, this is the formula which we will derive later in the course, and so it is not, it is more complicated. Okay. And the diffusion R squared was proportional to T in Langevin equation, but for atmosphere it is not T, it is, we know that, and we can, in fact, we can derive it, is T cube. Okay. So, this requires more work. No? So, the derivation of we need to bring in hydrodynamics and try to derive these relations.